Welcome to this first talk in this post-coffee session. The talk is by Amos Yarom, and he will be talking about holographic turbulence.
Great, thank you. So I'd like to thank the organizers for inviting me. It's always a pleasure to visit India, Bengaluru. And today I'm going to tell you about some work in progress together with Sebastian Weber, who's a postdoc at the Technion, and Yarom will be speaking on Friday. And like I said, this is work in progress. It's a long-term project I have where what we're trying to do is we're trying to get some information about incompressible turbulent flow from black holes. There are several stages to this project, which I'm going to sketch. We're pretty much at the end of the first stage. So some of this is really going to be a review of what, how exactly black holes are related to fluid flow. Some of you, I think, this is going to be boring for some of you, so I apologize in advance. When I try to give this talk in front of a mixed audience, I usually don't manage to get too far from explaining how fluids relate to black holes. But I think this is sort of the important part to understand in this talk. So if you have questions, please ask, and I'll do my best to answer. So the program is trying to understand turbulence from gravity. And there are three steps. So the first step is to generate a black hole which captures features of turbulence. It captures turbulent flow. So this is, we're sort of done with this part. It took us much longer than I expected. And I'm just outlining what the program is, and then I'm gonna say things in more detail. Second part is to try and identify geometric quantities which relate to turbulence. And then try to use gravity to predict them, or maybe say something about them that we don't know. So the attempt here is to really use gravity to infer something about turbulent flow, and this is the key to understanding how this is going to work is through this part. So this is technically hard. This part is conceptually difficult. And like I said, right now we're somewhere between 1 and 2. Okay. Let me start by just explaining what ADS space is. So let's look at this line element. Okay, so L is some scale. It's a fixed parameter. And I have here coordinates t, x, y, and z. So t, x, and y go from infinity to minus infinity, and you can see that the z coordinate special, it goes from 0 to infinity. So if this is my z-axis and I'm somewhere here at z equals 1, so suppose I just freeze my z coordinate to be at z equals 1, then if I'm sitting here at z equals 1, what I'll see is a line element which is going to look like this. So from the point of view of an observer looking at z equals 1, what he sees or she is just flat space. It's three-dimensional. It's a three-dimensional space-time with some overall factor which we can swallow in an appropriate choice of units. Okay, so if we freeze the z direction, we just see flat space. And if we look at a different value of z, and this other observer will again just see flat space-time. Okay, if we go from z1 to z2, what we'll see is some stretching, overall stretching of the entire space-time. Okay, so this is what this space-time looks like geometrically. Way out here at z equals infinity, we have here again something that'll look like a very big factor times this three-dimensional space. So this is called this is asymptotic infinity. And you can see that something weird is happening at z equals 0. It's not really important for this talk. This is called a Poincaré horizon. It's nothing special is happening there. It's just that the coordinate system doesn't really cover z equals 0, much like the origin of a polar coordinate system. Okay, so this describes anti-de Sitter space, or I should say a patch of anti-de Sitter space if I want to be precise. But again, that's not going to be, that information isn't really important for what I have to say. So this is anti-de Sitter space, and it's a solution to the Einstein equations in the presence of a cosmological constant. Questions so far? Okay. So much the same way that we have black holes in flat space, we can also have black holes in anti-de Sitter space. So planar black hole in ADS has the following line element. Okay, so it looks like this. So there's this extra factor of f in front of the time and z differential. And again, z goes from 0 to infinity. So if I have some value of z equals z1, which is big enough, then on this slice, we're again going to see just flat space time, and funny, maybe in some stretched coordinate system. But you can see that something funny is going to happen at z equals z0. So here at z equals z0, we have an event horizon, which is planar. So the event horizon is close to a Schwarzschild black hole. The event horizon here just stretches out to infinity. And z equals 0. Here we now have a real singularity. So this is just singular. And at large z, this factor is just 1, and we have the same behavior as before. So asymptotic infinity looks the same. So this behaves very similar to the Schwarzschild black hole that you're probably familiar with. Everything between infinity and the horizon is outside, and everything between the horizon and the singularity is inside. And once you're inside, you can't get outside. Usual story. And this, again, this is a solution to the same equation. Okay. Now, so this is well, one reason we were able to find, I mean, these equations are highly nonlinear. One reason we found the solution is because it's very symmetric, right? It's rotationally invariant and translation invariant in this direction, and has some other symmetries. So one of the reasons we can write down a solution explicitly is because of the symmetries that we required of the solution. If we now take something and throw it into the black hole, it's not going to look like this. There's going to be some, it's going to do something. The event horizon is going to jiggle a little bit, and whatever we threw in is going to fall into the singularity. And what we know is that if we wait long enough, then whatever happened here is eventually going to die out, and we're going to end up with a solution that looks like this, maybe with a different z-naught. So all this dynamics is captured by this equation, which we usually need to solve numerically if we want something that's not very symmetric. So we can try and make some sort of approximation to what the dynamics of this event horizon is going to look like, so that we can get a better handle over what it's doing if we perturb it. So the approximation that is going to be useful in this context is to say, well, let's consider fluctuations of this space-time where which are sort of where the gradients of the fluctuations are small in a sense. So we want to consider this solution as some 0th order solution in an expansion where quantities just change very, very slowly in space-time. So let's consider okay, so what this means is we start from this solution. This is a solution. We add to it another unknown term, but we require that this unknown term is going to vanish when gradients are small. And so we can plug this into the Einstein equations and expand perturbatively in this extra term we have here, and then see what we get. And that'll give us some black brane configuration where the event horizon is changing is dynamical, but at scales which are large. So I'm not going to do this. This is a longish computation, but it's something that you should all be able to do. It's just a perturbative computation. You plug in the right ansatz into this equation, and you see what you get. Yes. Well, I mean, I add a 3 + 1 dimensional line element here. And I make sure that the appropriate gradients are small. Who asked the question? Yeah, I'm skipping some information here because that's okay. Okay, so now you have to do this, and you have to do some massaging, and it's some work to do. But what one finds is that this equation is the same, I should reduce it to the following equation. Where, so Shiraz wrote this yesterday. Let's ask this let me just finish writing and then ask, because this T, the indices here are different. This is, let me just finish writing. This is a conservation law, but you're getting a conservation law from this equation. Well, it's hidden inside this equation. Yes, so the answer is yes. I'm not arguing. Okay, so here, this is a relativistic. So this is, E is some function of, so in a okay. Okay, so the statement is that, again, the Einstein equation is equivalent to, or reduces to this equation using the ansatz that I didn't specify, but I sort of sketched out. And the statement is that you get a conservation law of this type, where TMN is given by this expression here. So, and this is the equation of motion for relativistic fluid. So UM is normalized to 1, right? So usually we write UM to be this. We write something like this. So this is just the relativistic velocity. And this is the energy density. This is the pressure. There's an equation of state that tells us how the pressure is related to the energy density. And this is just this is a relativistic version of the shear. And this is what's called the shear viscosity. So, pardon? This is compressible. This is compressible. Right, so here, oh, and I forgot to say, can I write over this? No. Go back there. Okay, sorry. So let me just write it here so it'll all be together. So M runs over T, X, and Y, while mu, M and N the Greek indices run over this extra z direction. So even though, as you asked, the ansatz does include a z coordinate, you can somehow one can solve for the z dependence, and the dependence on the tx and y coordinates is here. Okay, so what this means is that if you give me a solution to these equations, then it's also a solution to these equations, again, in this approximation that we're using. Okay. So, sorry. Should I stick with the center?
No, that's all right.
Okay. So like you asked, we have here a relativistic set of equations, but one can show that there's a non-relativistic limit where this reduces to the Navier-Stokes equation. This? No, it's in Landau and Lifshitz. It's yeah. You can find this in Landau and Lifshitz. It's not, yeah. I mean, you can do, yeah. No. So I'm not sure exactly what you're asking. I mean, here when you take yes. So, but when I say there's when I say there's a non-relativistic limit, it means that there's a class of solutions which will look like this. You can have a non-relativistic limit which will be compressible. So I kind of hedged what exactly is going on here. So there are solutions which flow at velocities which are below the speed of light, and they're incompressible, and they satisfy this equation. You can also find other solutions which will be compressible. This is yeah. It's related to the viscosity over there.
How is it related to black hole?
So, I mean, here you have a viscosity. Okay, I'm sorry. There's a viscosity here. This is the viscosity that's associated with the relativistic flow. Right here.
Yes. How is it related to the black hole?
So, I mean, you want some intuitive picture, or are you asking for? Well, you should ask how is, so this is surprising, I should say. I mean, if you're not surprised by this, then this isn't trivial. It's not trivial that.
Is that arbitrary?
No, these are fixed coefficients. All these coefficients are fixed by the Einstein equations.
But what is
Viscosity? Viscosity, it's, so in this case, eta would be dp dt over 4 pi. I'm expanding around the black hole, around the black hole that's stationary. Yeah, so the black hole is an entire configuration. It's the entire space-time. The horizon is a submanifold, but I'm expanding the entire. I'm looking for a full solution to these equations. So yeah, the horizon is going to be perturbed a little bit, but the entire space-time is also going to have perturbations on it.
I don't understand how equation which expresses concentration of energy.
Well, here, I mean, when you look at the relativistic fluid, then, this is the energy isn't just the kinetic energy. The total energy is T00. So heat, what you would call heat, is already incorporated into this energy momentum tensor. It's the momentum tensor of the entire thing. I have a fluid that's filling my entire space-time, and the energy momentum tensor of the entire system is given by TMN. Okay, so it.
Einstein equations are time reversed. How you get time breaking of time reversal starting from the time metric equation?
So I mean, again, this.
Because you're working with black holes rather than white holes. Things fall into the black hole.
Yeah.
And they don't come out. That breaks the cycle.
You're looking for, yeah, I mean, maybe it's related to what Grisha was saying. Here, this isn't general. This won't happen no matter what you do. We're looking at a particular perturbation of a black hole. So you need the black hole to be there from the start, and then you're perturbing around it in some small sense. Okay, so you're perturbing around this black hole, and then you ask, what are the dynamics? And it turns out that the dynamics are given by this equation.
So black hole, by background existence, breaks time reversal.
Yes, things can't come out. Okay.
Hello, Amos. Yeah. Could you just indicate where the parameters have gone in the L and the Z naught?
Pardon?
The parameters of the parent, the unperturbed black hole, the L and the Z naught, where all have they gone in exactly?
Yeah, so it's going to be related to L you can factor out from the equations. So there's an L squared that you can really set to 1, it factors out. Well, it sets a scale. So, and Z naught appears in defining what epsilon and P are relative to L.
I was asking for the expressions if you have them, if they're
Explicit
simple enough,
ones?
I don't know.
You can do that after.
Yeah, sure. Yeah.
It's some power of Z naught, which we can figure out by dimensional analysis times some number. So it's not something complicated. Yeah, okay. Okay, so now what this means is that if we have a solution to this equation, and in it is an approximate solution to the full relativistic equation, then we can just plug that into this ansatz, and it'll also be a solution to the black hole. So in particular, if we have a turbulent solution to the non-relativistic Navier-Stokes equation, then we should be able to have a black hole which captures that information. Okay, because it's all a mapping of solutions. Okay, so one thing people did was just to try and find a turbulent solution using just starting from exactly this setup. So they solved these equations, they solved the full equations, but their initial conditions were such that they started off with a small perturbation of a black hole, and they could see some turbulent flow. It was decaying turbulence because there's no driving force here to keep it in a steady state. And well, this is, first of all, this is going to be fluids in 2+1 dimensions, so 2 spatial dimensions. So the dynamics are a little different from what we're used to in 3+1 dimensions. I'm sure you know better than me. And it's decaying turbulence, so it's really hard to say something very definite there. So
when you say they found, they found numerically?
Numerically. I mean, analytically, there's nothing to find. It's, yeah, numerically, yes, yes, yes. Okay, so
Black hole, one more spatial dimension, like 5-dimensional Minkowski, you will get 3-dimensional curve.
yes, yes. The problem is that the price you pay is that if you're doing this numerically, you have an extra dimension. So if you want to look at fluid flows in 2 space and 1 time dimensions, you have a 4-parameter.
That's
Yeah. So exactly. So the reason they did it, also we do it for 4-dimensional space-times or 2 spatial dimension fluids, is just that it's computationally intensive. Okay, so what we want to do is to find some sort of steady state turbulence. We need to add some sort of driving force, and we want to add it in a way which would be consistent with this whole setup. We don't want to add it by hand. We want it to be somehow incorporated in this equation. So what we're going to do is to add a stochastic term to the boundary, the asymptotic boundary of space. So I'll write this first. Okay, so what this means is that we have an initial black hole, which looks like this. And here, we want the line element asymptote you don't have to do it this way. Okay, so we want the line element at infinity, at t bigger than 0, not to look like, not quite to look like Minkowski space, but to take this form where q is a random variable. Yes. No, because we need once you insert this q, then you have to start taking time derivatives of it. And then if it's white noise, it's not really well defined. So we use some sort of, I can write it out. I won't remember it off the top of my head. It's not white. It's sometimes called an Ornstein-Uhlenbeck process. Yeah. Okay. Yeah. Okay. So that's where Q is drawn from. You don't have to make it. You don't have to use this component. We tried several other things. I'm saying this because I'm using this because it's going to be sort of easier to say what's going on physically. So once you do this, what happens is that the mapping, in this case, the Einstein equations reduce again to this, right? But now this derivative is in a space-time which is fluctuating. So there are Christoffel non-trivial. There's a non-trivial Christoffel connection. Right? It's in this space-time. And if we take the non-relativistic limit of this, then what we'll get is a non-relativistic fluid that's inside some stochastic gravitational potential. So we have some random gravitational potential, and that's what's driving the fluid. Yes, it'll translate into a forcing term.
Just additive force.
There are multiplicative terms, But when you take the non-relativistic limit, you get just that. So if it's linear enough, you won't have multiplication. Yes, yes. Well, it's a gradient of an Ornstein. So it's up to us. We have some. We put it in some. We put it in some. Who asked the question? Sorry. We put it in some scale. We drive it, the usual way. We have some in momentum space. It's around some ring, which we call. No. So, I mean, what's happening here at infinity, you're right that it's at infinity in some sense, but we can still tune. So this is the z direction, but we can still tune how q is fluctuating in the t and x and y directions. That's completely up to us. Okay, so I'm just going to give you the punchline. Yeah. Let me just stop here. Okay, so what we did was that, and okay, there are so many technical challenges here that I'm not going to even say them. This is much harder than I thought it would be. It's because essentially you want a stochastic version of the Einstein equations, which are highly nonlinear, and you have to worry about things that I wasn't aware of. But at the end of the day, we run the numerics. And there's some fine print here, but in the end, we can compute numerically again the power spectrum, and you really get this. You get an inverse cascade minus. Numerically, Einstein. All we do is Einstein. Right, and we get something like 0.77. And there's some other measures that we looked at. There are issues here that I just don't have the time to get into that have to do with something you asked about, whether it's really incompressible or compressible. There's some issues we're still trying to work out. But this looks like it's really, well, this is one of the hallmarks of turbulent flow. So it looks like we do have an actual solution starting from here, which is turbulent. And my time is up. But the next stages of this program is to really try and determine this coefficient from these equations using some techniques about evolution of the horizon. So I'll stop here. Sorry for going over time. Yeah, that's a good question. So that's at this point, none. At this point, there's no advantage. You actually have to work harder to solve this equation because you have an extra direction. Yes. So you have, and also, but technically you have an extra direction. So your grid has one dimension more. Okay. So there's, at this point, there's no advantage. Okay. But the advantage is, well, the presumed advantage would be that we have a geometric way of encoding this. So this is the part of the program that's more conceptual. So we have some ideas. For example, you can relate the dissipation rate to the extrinsic curvature of the horizon. And so averages of the dissipation rate would correspond to averages of the curvature of the horizon. And there are equations that tell you what the extrinsic curvature of the horizon is doing. And hopefully they can tell you something about extrinsic curvature. Yeah, it's extrinsic curvature squared, and that'll give you sigma squared. Yes.
So, yeah, it's like an immediate question. This is two-dimensional turbulence, right?
Yes.
Where do you get this exponent, which is so different from what we know from 2D turbulence?
So this is an inverse cascade.
Sorry, what's the number there? K raised
1.7.
1. Oh, okay.
Yeah,
oh,
instead of-
I couldn't see. Oh, okay, so that's a good thing. Okay, disregard my question.
It's
then.
close. We have big errors. I mean, our numerics are, yeah.
You get a stationary state?
That's exactly what I would want to do. That's the next step of the program. So one thing to look at would be the extrinsic curvature. There are some arguments on the market that say that the event horizon should have some sort of fractal structure, at least in the inertial range, and the fractal dimension of the horizon would be related to this. And again, that's something that the evolution equation should tell you. So that's exactly what I'm trying to do. This took 2 years. I mean, it took just getting the numerics here. You're not very good numerics took me longer than I thought. It's 1 decade.
Sorry for the stupid question, but there is no leakage and coupling at all with the third dimension?
Sorry?
There is no leakage or coupling at all with the third dimension, with Z?
What do you mean by leakage? In what sense?
I mean, there is no coupling at all with the third dimension. I mean, it's you have a closed equations in 2D.
No. Our equations are in 4D. Our
Yeah.
equations are in 4D, and we solve these equations where the Z coordinate is coupled to everything else. But we know from analytic results that in the limits that I sort of glossed over, they will decouple. So we know that they should decouple, but we don't make that assumption a priori. We just solve this.
Perhaps we should move on to the next talk and continue this discussion during the lunch break. So the next speaker is Shamriddhi Shankar Rai from the ICTS. And I'm not sure the title of the talk that he's. So he will.